Polyprotic acids. So what are polyprotic acids? They are acids with more than one ionizable proton. Before we look at a few examples of them, I want you to know that the Ka, remember the acid dissociation constant? Polyprotic acids have different Kas each time a proton is donated. So maybe we'll correspond that over here. There are different Kas each time a proton, and when we say a proton, we are dealing with the hydrogen ion, right? So each time a hydrogen ion is donated. So for example, Ka1 is going to be greater than Ka2, and it's going to be greater than Ka3. So we only really use this one, okay? We only use this one. Since Ka2 and Ka3 are insignificant. Because they are weak. And you're going to see this in a practice problem a little bit later on. Therefore, equilibrium is really only maintained by that first value of the Ka, Ka1. Okay, so equilibrium is mainly maintained established/maintained by Ka1. Now let's have a look at those examples that I was talking about. So the first polyprotic acid that I want you to know of are diprotic acids. Okay, diprotic acids have two protons to ionize. Whereas something like a triprotic acid, and we're going to look at that in the next example shortly, they have three. Obviously, tri means three, so three protons to ionize. Regardless, all of these types of polyprotic acids need to ionize in steps. Let's have a look at a triprotic acid. So let's have a look at H3PO4. You should know that this is phosphoric acid. So let's here put it as an example. So if we use our H3PO4, our phosphoric acid, obviously it's going to be aqueous because it needs to dissolve in water. So if it's aqueous, we're going to have to put the other reactant as water. It's going to be liquid, so they're going to dissociate. Okay, it's going to break apart. What do you end up getting for ionization? Your respective cations and anions. Now, of course, this is an acid, so it's going to donate a proton. So this 3 over here is going to get donated. And of course, this H2O is going to receive that proton. So if this donates it, this is going to then become just an H2. We have one less hydrogen. All right, so we have one less proton, so we're a little bit more negative right now. So there we have that. Now we're going to be putting our little AQ because it dissociated, and then we're going to get this as our hydronium because it received that extra proton. Well, now we can establish what our Ka1 is going to be, because this is going to be our first one, right? So our first step in making sure that we get rid of all of these protons over here. This is our first step, so we're putting it as labeling as K1. So our K1 is going to equal, obviously, always, like any other equilibrium constant, our protons, sorry, our products on the top and then our reactants on the bottom. So we have our H2PO4. And then we're going to multiply by our hydronium. And then on our bottom, we're going to have our H3PO4. There we have it. So our Ka value, if you were to get it all from a data table, it ends up becoming 7.2 times 10 to the negative 3. Now, if we were to flip this and do it as a Ka2 expression, what do we end up getting? Well, now a second proton, so the hydrogen ion, needs to ionize. But unlike the relationship of Ka and Kb and Kw in the previous video, where the conjugate base acts as a base, this time the conjugate base doesn't act as a base. But rather as an acid, again, like this one over here. Why? It's to ensure it can donate H pluses again continuously. So let's have a look. We have our H2PO4. This here, remember, is our conjugate base. This, like I always established, was our acid. This, when it removes that proton, what is left over, what has formed after that hydrogen got removed, it becomes our conjugate base. We've seen this in our previous videos repetitively. So this here is a conjugate base. We're not going to be putting it here, but we're not going to make it act as a base. Okay? Not act as a base, but rather as an acid again. So we're going to add it with water again. So rather than this acting as a base, I know this is our conjugate base right now, but rather than acting as a base, we're going to make it act as an acid. So of course it's going to donate one again, okay, towards this H2O. It's going to donate another, so it's going to become H, just one H, PO4. And of course, got rid of one more proton, so we're even more negative. Okay, so we're not at a -1, we're now at a -2. And then we're going to add this with our hydronium that's been formed from our liquid water. There we have it. Now we're going to be doing our Ka, but this is for our second step. And for our Ka2, it's going to be HPO4. And then we're going to be multiplying it by our hydronium over here. And then we're going to divide it by our H2PO4, 1 minus. And then what do we end up getting for our value for our Ka2? If we can get it from a data table and plug it all in, you end up getting a value that is smaller, 6.3 times 10 to the -8. Let's move on to the third one. So I've written it out over here, our Ka1, our Ka2 from the previous steps. Now let's look at our HPO4 2 minus, because this one here was what was formed after that very last Ka2 expression. So that H2PO4 1 minus created our conjugate base here, HPO4 2 minus, and now this HPO4 2 minus is going to do the same thing. So this one is going to create now its own conjugate base. Again, this acts as an acid. It needs to get rid of this last proton. It is polyprotic. Sorry, it is triprotic. Got 3 of those hydrogens, so we just got 1 more left to finish off and donate and act as an acid. So that means we're going to get our conjugate base over here. So we remove that H, we end up getting PO4. Oops, 3 minus. And of course, we know that this is our phosphate polyatomic ion that you've learned in previous grades. And then this one gets donated here. This becomes another hydronium ion. There we have it. So we're going to be putting our Ka3 as our products over here. And our H3O plus. And of course our reactant HPO4 2 minus. Again, you should be knowing why this H2O is not included in the Ka. See the link in the description if you have no idea about where this went. Okay, we did go over this many times throughout the series, so have a look at that video in the description if you need more help on this. So we have this done. We have our PO4 3 minus, our phosphate on the top, we have our hydronium, and then we have this HPO4 2 minus at the very bottom, our last reactant. And then we end up getting, if you use the data table, our Ka value becomes even smaller than the previous, 4.2 times 10 to the negative 13 actually. So if I add this up here, you end up getting, you get 4.2 times 10 to the negative 13. And as you can see, it is decreasing as we go down. Why? Okay? Well, first we have to know what is the strongest. And remember, the higher the Ka value, the stronger the acid it is. So I'm just going to put here in case you forgot. Okay, the strongest acid has higher Ka value. This means this one here, which was our phosphoric acid, or H3PO4, okay, in case you forgot, maybe we'll put it over here. This Ka1 was H3PO4. This one over here was H2PO4. Oops, 1 minus. And this one here, what we just did was our HPO4 2 minus. So obviously, this one here is going to be the strongest. Why is it the strongest? Because it is easier to remove hydrogens from this, a neutral atom, than it is to remove a second or third proton from a negative ion like this, or from a negative ion like this. I'll explain why. Let me write this down here first on the side in a little star. H3PO4, phosphoric acid, is the strongest acid. Since it is easier to remove H plus, our proton, from a neutral atom. Obviously that's neutral because there is no charge on it. Than it is to remove from a second or third negative ion. So this here and this here are the negative ions. How is this possible? Well, hopefully you remember from the beginning series when we looked at matter and bonding that ionization energies can be a similar analogy over here. So here I'll just put example, ionization energy. The video link is in the description in case you need a reminder about that. For ionization energy, for example, if I had, let's say, a silver over here, and energy is given to it, how much energy is needed to remove that electron from the outermost shell? Well, if we receive this energy and it releases that electron, it's enough energy to get rid of this electron from that outermost shell. What's going to end up with our Ag? Well, our Ag here Remember, it used to have this electron, but we gave it energy, hence why it's on this reactant side. We gave it energy over here. Okay, we gave this energy to the silver, and it was enough energy, suffice energy to remove this electron. So we don't have this electron anymore, okay? This negative is gone. So we're going to be actually a little bit more positive now, okay? Compared to its ratio of protons that it had before, okay? So it has a certain amount of protons, has a certain amount of electrons. We get rid of one electron, so it's going to be a little bit more positive right now. So this ends up becoming Ag+. Okay? And if we were to do this again and use this one over here, and we do the same thing, we give it even more energy so that we can get rid of another electron from here. So another electron is left, so now it becomes even more positive. So instead of Ag1+, it becomes Ag2+. And we looked in that video that this one over here has a higher amount of ionization energy. It's going to be more difficult. The amount of energy to remove this electron from that last shell, it's more difficult to do it here, okay? It's actually easier in the beginning, okay? It's easier up here where it's more neutral, as opposed to here where it is not neutral, okay? It is a positive cation over here. So it's the same thing here, okay? It is the stronger acid at the beginning when it is neutral because it is easier to remove the H+. Okay, here it's easier to remove the H+. Here it's easier to remove that electron. Okay, just this one's dealing with the proton. This one here is dealing with the electron. Now you should also remember that in our ionization energy, this one over here, because it is neutral, when this electron goes away, there's going to be less electron to electron repulsion. So if you remember from our Bohr diagram, we had protons on the inside, we had our neutrons in the middle, and then of course we have, you know, our electrons on the outside. If you have an electron and it is gotten rid of, okay, so let's say this one here, it's gotten rid of, okay, so this is gone now. So all we have is just one electron right now. This electron here doesn't need to fight with this electron anymore. Okay, so this electron has no competition, so it's going to be easier to go and stay closer to this proton as much as possible because it doesn't have this electron to electron repulsion with this guy over there. Okay, so this one here is going to be a lot happier when this electron is gone. Okay, it's going to be able to kind of be closer towards that proton. Okay, hence why it's going to be more easier for this electron to stay with this neutral atom. And as we go later on with our cations, the more electrons that are removed, hence why it becomes more difficult. When there were two electrons over here, okay, when there were two electrons, it's easier to take it away because right now it's a little bit more neutral. Okay, right now this here is neutral. Okay, so if it's neutral right now, because we don't know how many protons are in here, but let's say it's neutral, so let's say there's 2 protons in here, okay? Just the general outline over here. If this is neutral right now, it's going to be easy to take this away because there's a lot of repulsion, okay? And we haven't even added in our shielding effects. We haven't added in extra shields of electrons in the middle, okay? I'm just saying right here in this example, these 2 electrons right now, okay, do not like each other. So if you were to get rid of this electron, it is actually relieving this tension, okay? So when we get rid of this electron, it's going to be a lot easier. However, if this is gone, okay, then it's no longer going to be neutral. Okay, this is now going to be a negative ion, and now we have this electron that is not having to compete with any neighboring electron. It's closer to the protons in the middle here and doesn't have to share. Okay, it kind of has these protons near it to itself. So of course that's kind of like translated over here. If we want to get rid of this electron now, it's going to be more difficult because it has less competition. It's very, very close to this proton. Okay, so to get rid of this is going to be hard. Okay, it's going to be extremely difficult, as what we can see over here. It's going to be similar to this one over here. Okay, I know we were dealing with electrons over here, but even when we're dealing with protons, it's kind of the same concept. If you have protons in the middle, right, and we have, again, a lot of protons in over here, remember, protons repel each other as well, okay? So if these protons do not like each other, they want to be separate from each other, in the beginning it's going to be easier to remove them, okay, because there's going to be a lot of them repelling. However, if you remove one, let's say, okay, we removed one proton, there's going to be less inside here. There's going to be less protons now. Okay, now that we have less protons, there's going to be less repulsion. If there's going to be less repulsion, it's going to be more difficult to get it from a second or third negative ion, okay? Because remember, once we removed one proton, now this here is a little bit more negative, right? It's a more negative ion right now. So from now on, if we wanted to get another, okay, we wanted to get another proton from here, it's going to be difficult because there is going to be less less proton to proton repulsion right now. So it's going to be more difficult to take it away. We have 0.040 moles per liter of H2CO3. We know a formula is pH is equal to negative log of our hydronium ion concentration. And we can continue to solve this using our Ka1 and Ka2 values. Well, we know that our Ka means that it is an acid dissociation constant. And if this is an equilibrium dissociation constant expression, right, we always have our products on the top and reactants on the bottom. In that case, we should do an ice table. So we're going to be putting our reactants here, our products over here. So again, before we write it on over here, let's do our H2CO3. This was our polyprotic acid. And we add it with H2O. This one donates it, so it becomes HCO3. 1 minus aqueous. And this here becomes our hydronium ion. What's going to happen now? Well, these are our products. This is our reactants. So let's put our H2CO3 here. H2O over here. These all remain constant. Then of course this becomes HCO3. 1 minus, and this becomes H3O plus. So for H2CO3, they say that there is 0.040. And again, this is all going to be in moles per liter as a disclaimer. And then this and this not produce it, so we'll just count them as 0. And based on our little equation that we created, we have all of them as just one coefficient, so it'll be just negative 1x. These get gained, so they become a positive x. And then we just bring this down. This is our 2x's. This becomes 0.040 minus x. So we can do our Ka is equal to our products on the top, x times x, gets us our x squared, and this becomes 0.040 minus x. Now, remember, our Ka value here, what is it? Our Ka value was a value of 4.3 times 10 to the negative 7. If that's the case, and instead of keeping this x down here, which is going to make our life more difficult to create a quadratic formula, can we assume that this is going to be greater than 1,000 rule, so that we don't have to do this and actually just shorten it and simplify it where it's just 0.040 as a denominator. Okay, so does the greater than 1,000 rule work? Well, let's have a look. Well, we have our 0.040 moles per liter. We're going to be dividing it by our Ka value of 4.3 times 10 to the negative 7. Again, if you have no idea why we're doing this, see the video link in the description about the greater than 1,000 rule. So this is, again, times 10 to the negative 7 over here. And then we just divide them. What do you end up getting? I'm getting 93,023.26. That means this Ka value is so small, okay, it's such a small value that we don't have to be putting 0.040 minus x. We can just keep it as 0.040. Okay, so we're going to be, instead of doing this, bring this one over here where we have our 4.3 times 10 to the negative 7 is equal to our x squared, and now we're just going to simplify it to 0.040. Okay, so now we can just quickly cross multiply here, okay, or if you want, multiply this side by 0.040, You can also do the same thing here, multiply by 0.040, what you end up getting for our x squared, getting 1.72 times 10 to the negative 8. Bring this over, what does our x become? You end up getting 1.3114 times 10 to the negative 4, okay? So this here is obviously going to be our x values over here. Now that we got our x value, we can assume that this here is going to be our H plus. Why? Because remember our formula for our pH. We eventually need to find the pH in this question, right? We need to get our H plus, okay? Our H plus is going to be seen as the hydronium, right? H plus, hydronium, they are going to be the same. So whatever value I got for x, which is this one over here, okay, I can plug it in as our H3O plus, which is the same as our H plus over here, so I can just put that value in over here. Okay, what did we get for x? We got 1.31149 times 10 to the negative 4. And then this is going to give us our pH. Okay, what is our pH going to be? We end up getting 3.89. Okay, so we found out our pH. If you want to find the concentration, I know it's saying find the concentration of all the species, okay? You could actually find the concentration of the next species. So again, we did this as our conjugate base, right? This here was our acid, this was our conjugate base. So if you wanted to do it for the next species, so we can just bring this over here. And we can add it with water and do the whole same thing again. So this one loses it. Okay, so now we have no hydrogen over here. We get one more negative over here because we're a little bit more negative now. And then we get our hydronium. So if we wanted to find the concentration of this one over here, it's actually going to be the same. Okay, weaker acids don't dissociate, okay, or they barely dissociate, so it's about the same. So this value over here, how are we going to find the concentration of it? Well, if it says our Ka value was 5.6 times 10 to the negative 11, we could actually say that the concentration for this one over here, the concentration is going to be the same, 5.6 times 10 to the negative 11, because again, our Ka value here is so low, and like I said previously in this video, we only really care about our Ka1s, okay, our Ka2s, our Ka3s, okay, if there was a Ka3 value here, okay, this one and this one, we don't really use it, we only focus on this one, okay, these are technically negligible, okay, so the concentration for a CO3 2- is going to be this concentration down here. I also want to show you over here that these are just more further proof of references that you can use of our Ka1, Ka2, and Ka3 for these different types of acids. As you can see with the trend, they continually decrease as they go further down. Okay, so it's strongest up here, gets weaker down here, and it gets even smaller down here. Same thing here. Biggest, next weakest, and then the weakest, biggest, and weakest. Okay, so this is a good chart that you can use as well. And this here is our green question of the day. Okay, please give this a try on your own, and I'll be giving you the answers shortly. This is the answer.